Platinum is often spoken of in the same breath as gold and silver, but it stands apart as one of the rarest and most valuable metals on Earth. This silvery white metal has an undeniable prestige. In fact, the word platinum has become synonymous with exclusivity and high status. Think of platinum credit cards or music records. But why exactly is platinum so expensive? The answer goes far beyond its use in jewelry. Platinum's value is tied to its fascinating history, unique physical and chemical properties, scarce occurrence in nature, and a wide range of important applications in modern life. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe, and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, when we will again probably not choose zinc, so why do I even bother to put it in the poll? Now, we are of course disappointed that zinc lost the poll again, but the good thing is that this element of today is not looking like another lanthanide. And it is fair to say that it is a very appealing cube with the shiny parts in it. I'd like to introduce to you platinum. Now it kind of looks as if somebody put aluminum foil in the cube, but this is actually platinum. So let's get to the segment you all been waiting for. Can you lick it? Again, using the periodic table, which we will, like mentioned, rewrite at some point in the future, it states, go for it. And in this case, we agree. Yes, you can lick pure platinum safely in small occasional amounts, like actually many people do. Because platinum is a biocompatible and non-toxic metal. It's considered inert, meaning it doesn't readily react with bodily fluids or tissues, and that's why it's used in medical implants like pacemakers and dental crowns. Now, if you want to collect platinum or any of the other elements like us, click on the link in the description, use the promo code, get a 10% discount, and you will also be helping out our channel. The very name platina has its roots in Spanish. In the 16th century, Spanish conquistadors in the New World encountered an unfamiliar white metal mixed in the river sediments, as they panned for gold. They dismissed it as an annoyance. It looked like silver, but it wouldn't melt or behave like the metals they knew. The Spaniards mockingly called it platina, meaning little silver, because of its silvery appearance and seeming inferiority to real silver. They viewed it as unripe gold or a nuisance impurity and often discarded it while mining for gold. Little did they know, platina would one day become more valuable than gold itself. Traces of platinum had actually been used long before the Spanish named it. Archaeologists have found small amounts of platinum in ancient Egyptian artifacts. For example, a tiny box from a burial of an Egyptian high priest was decorated with a gold-platinum alloy. However, the Egyptians did not recognize platinum as a distinct metal. It was likely present unintentionally, and they lacked the means to work or identify it. Meanwhile, across the ocean, the indigenous people of South America were the first to deliberately use platinum. As early as around 500 BC, cultures in what now is called Ecuador and Colombia worked with platinum. They encountered natural occurring nuggets of platinum mixed with gold in alluvial river deposits. To craft jewelry and ceremonial objects, these pre-Columbian artisans developed a technique of mixing platinum dust with gold and sintering, heating, without fully melting the metals together. The result was a workable gold-platinum alloy with a bright white shine. Now, these artifacts astonished modern archaeologists because pure platinum has an extremely high melting point and was thought impossible to melt with ancient technology. By alloying it with gold, those early metalsmiths found a clever workaround to utilize platinum's beauty. For 2 centuries after the Spanish first encountered platina, the metal remained a laboratory curiosity in Europe. In 1557, an Italian scholar named Julius Caesar Scaliger made the first European reference to platinum. He described a mysterious noble metal from the New World that couldn't be melted by any heat or Spanish artifice. Despite such reports, platinum was not widely studied at the time, partly because it was rare and found only in far-off Colombia, and partly because European metallurgists had no easy way to process it. Now, it wasn't until the 18th century that platinum truly captured scientific attention. In 1735, Spanish explorers Antonio de Ulloa and Jorge Juan encountered platinum in Colombia during a scientific expedition. Ulloa is credited with bringing samples of platinum back to Europe and is often named as the discoverer of platinum in European history. He published a report in 1748 describing this strange new metal, noting its resistance to heat and chemicals. Around the same time, other scientists got their hands on Colombian platinum and began investigating it. In 1741, British metallurgist Charles Wood sent a sample of platinum ore to William Brownrigg for analysis. Brownrigg presented the paper at the Royal Society in 1750, detailing platinum's properties. He marveled at how it resisted even the highest furnaces and did not melt, and remarked on its unfusibility. We now know that platinum actually can melt, but at a much higher temperature than any standard furnace of that era could reach. In 1752, a Swedish chemist named Henrik Scheffer published one of the first comprehensive scientific studies of platinum, calling it white gold. Now, Scheffer managed to partially melt platinum by mixing the ore with arsenic, which forms a lower melting alloy. He found that platinum to be exceptionally resistant to corrosion, similar to gold in its nobility, but also noted that it seemed less malleable than gold. Early experimenters often found platinum hard and brittle, but unknown to them, this was because naturally occurring platinum from mines was not pure. It contained small amounts of other platinum group metals like iridium and osmium, which made the metal brittle. Pure platinum is actually quite soft and very ductile, meaning it can be drawn into wires, but that purity wasn't achieved until later. Throughout the late 1700s, scientists struggled to find methods to refine and work platinum. Carl von Sickingen in 1772 discovered that alloying platinum with gold, then removing the gold by dissolving it in acid, left behind a spongy platinum that could be pounded together. Another researcher, Franz Karl Ackart, made the first platinum crucible, a heat-resistant container, in 1784 by fusing platinum with arsenic, then driving off the arsenic vapors. These early methods were complicated and dangerous, but they produced malleable platinum metal in small quantities. A major breakthrough came thanks to a patronage of a king. In 1786, King Charles III of Spain set up a laboratory for a French chemist named Pierre-François Chabanous, specifically to crack the platinum problem. Chabanous toiled to purify platinum ore that was notoriously mixed with various impurities. After many failures and months of effort, he succeeded in removing contaminants like gold, copper, lead, and iron from the Colombian platinum ore. Unknown to him, some impurities were actually other platinum group elements like iridium and osmium, not recognized as separate metals at the time. These hidden elements caused inconsistencies in result. Sometimes his platinum was soft and workable, and other times it turned hard and even volatilized when heated, depending on which impurities were present. Now, eventually Chabanous figured out how to produce relatively pure malleable platinum. Legend has it that by hammering and compressing heated platinum powder, he consolidated about 23 kilograms of pure platinum, an impressive amount in that era. With this supply, Chabanous and partner established a workshop in Spain making platinum ingots and utensils. They crafted royal gifts and scientific instruments from platinum. One reason platinum remained so expensive was the scarcity of known sources. For a long time, the only significant source of platinum were the alluvial deposits in Colombia. Now, as those surface deposits were exhausted by mining, supply became very limited. But by the early 19th century, new discoveries shifted the balance. In the 1820s, a substantial platinum deposit was found in the Ural Mountains of Russia. These were also placer deposits, loose grains in river sand and gravel, similar to the Colombian finds. Russia quickly became the world's leading platinum supplier during the 19th century. The Russian platinum was abundant enough that Russian Empire even took the extraordinary step of minting platinum coins. From 1828 till 1845, Russia issued platinum ruble coins in 3, 6, and 12 ruble denominations. The first time in history a major currency was made from platinum. This was possible only because the Ural mines provided a windfall of the metal. Meanwhile, scientists and engineers developed better technique to extract and work platinum. By the mid-19th century, the flame of a hydrogen-oxygen torch could reach high enough temperatures to melt platinum outright. This opened the door to easier fabrication of platinum objects. Platinum found use in scientific apparatus. For example, the British scientist Sir William Wollaston, who also discovered palladium and rhodium, famously made fine platinum wire and crucibles for chemistry. Wollaston had a secret chemical method to separate platinum from its ore, involving dissolving in aqua regia acid and precipitating ammonia chloroplatinate. With such methods, platinum could be produced in greater purity and quality, albeit still small by today's standards. The true explosion of platinum production came in the 20th century with the discovery of huge platinum ore deposits in South Africa. In 1906, platinum was found in Transvaal, South Africa, and in 1924, a geologist named Hans Merensky identified an enormous geological complex rich in platinum and related metals. To illustrate how dominant South Africa is, even now around 70 to 80% of the newly mined platinum each year comes from South African mines. Other significant sources include the large nickel-copper mines in Norilsk in Russia and Sudbury in Canada. These mines primarily exist for nickel and copper, but they contain small amounts of platinum group metals as byproducts. Geologically, platinum is incredibly scarce. It's considered one of the rarest elements in the Earth's crust. On average, platinum is present at only about 0.005 parts per million in crustal rocks. To put it simply, there's only a few parts per billion of platinum out there, far less than most common other metals. For comparison, even gold is a little bit more abundant in the Earth's crust than platinum, though both are very rare. Platinum tends to occur in certain ultramafic rock formations, ancient magma chambers, and is often found alongside other platinum group metals like palladium, rhodium, osmium, iridium, and ruthenium. A key platinum mineral is sperrylite, platinum arsenide, especially in the nickel mines of Sudbury, Canada, which yields platinum as a byproduct. Another important platinum-bearing mineral is cooperite, a mixed platinum-palladium-nickel sulfide found in the Merensky Reef in South Africa. Now, extracting platinum from its ore is an extraordinarily complex and costly process, which is a major factor in its high price. To visualize the challenge, typically 7 to 12 tons of ore might need to be processed to obtain just 1 ounce of pure platinum. In other words, gigantic loads of rock have to be mined, crushed, and refined to get a tiny amount of metal. This is far more labor-intensive than mining many other metals. For example, gold might be found at a few grams per ton of ore. Platinum can be even less. Mining operations for platinum often resemble those for other precious metals. In South Africa, for instance, miners go deep underground, nearly 2 miles deep in some cases, following thin veins of PGM-rich ores. In other places, like Russia or Montana, platinum is a byproduct. The mining is focused on nickel or palladium, and platinum comes out in the mix. In either case, once the ore is extracted, it is first crushed into fine particles and then concentrated. One common method is froth flotation, where the ore is mixed with water and chemicals so that platinum-containing minerals float to the top for collection. After concentration, the next steps involve pyrometallurgy and hydrometallurgy, essentially high-temperature smelting followed by chemical processing. The concentrate might be melted in a furnace to form mate, a molten mixture, from which iron and sulfur are removed, leaving behind a mix of platinum group metals plus some base metals. This mix, often called PGM concentrate, doesn't look like shiny platinum yet. It's a very impure alloy or sludge. Refining this to pure platinum requires multiple chemical steps. One classical approach, pioneered by Wollaston in the early 1800s and still used in principle today, is to dissolve the metals using aqua regia, a mixture of nitric acid and hydrochloric acid that is one of the few reagents capable of dissolving platinum. In aqua regia, platinum will go into a solution along with gold and palladium, while some other metals like iridium, osmium, and rhodium might remain solid. By carefully adjusting chemicals, refiners then sequentially precipitate out the metal. Now, for example, by adding ammonium chloride, platinum can be precipitated out from the acid solution as solid compound called ammonium chloroplatinate. When this salt is heated strongly, ignited even, it decomposes to leaving behind spongy elemental platinum. That platinum sponge can then be melted under high heat, often in an electric furnace, or with an oxy-fuel flame to cast ingots of pure platinum. It's worth noting that the separation of platinum group metals is one of the most difficult refining jobs in metallurgy. These elements are chemically quite similar to each other, so it takes a lot of sequential treatments to tease them apart. Each additional step contributes to the cost. Now, in pure form, platinum is a lustrous silvery white metal. It is known for its beautiful sheen that doesn't fade or tarnish. Unlike silver, platinum doesn't easily form surface oxides or sulfides, so it stays bright and shiny over time. This makes it highly desired for jewelry and decorative uses, since platinum jewelry can maintain its luster for generations with minimal care. Platinum is also extremely dense and heavy. It is one of the heaviest elements, about 21.45 grams per cubic centimeter. To put that into perspective, platinum is nearly twice as heavy as lead and even denser than gold. A small bar of platinum feels very hefty in the hand. Even a ring made of platinum will feel heavier than a gold ring of the same size. This density contributes to the sense of substance and quality of platinum objects. Now, we touched upon this briefly, but platinum's most outstanding attributes is its resistance to heat and chemical attack. It has a very high melting point of about 1768 degrees Celsius or 3214 degrees Fahrenheit, and that is much higher than the melting point of gold, 1064 degrees Celsius, or even steel. Platinum doesn't boil, turn to vapor, until an astonishing 3825 degrees Celsius. What this means, practically, is that platinum can withstand and function in extremely hot environments. Now, if you heat platinum in air, it doesn't form an oxide scale or burn. It remains metallic and bright even at white-hot temperatures. Also, very few chemicals can corrode platinum. Acids like hydrochloric, nitric, sulfuric acid alone generally do not dissolve platinum. Only certain mixtures like aqua regia, which we just mentioned, or certain molten salts can attack. Now, because it is chemically so inert and stable, platinum containers can hold corrosive chemicals or be used at high temperature experiments without contaminating the contents. This corrosion resistance is one of the reasons platinum was chosen historically for standards like the kilogram mass and the meter bar. More on that soon. Platinum is sometimes called a noble metal, a term used for metals that resist oxidation and corrosion. Others are gold, silver, to a lesser extent, and the platinum group elements. However, platinum has an interesting twist. While very unreactive in bulk form, it is an excellent catalyst for chemical reactions. Finely divided platinum, platinum black or platinum sponge, can speed up reactions such as the burning of hydrogen or the breakdown of pollutants, without the platinum itself being consumed. This ability comes from platinum's surface properties at the atomic level. It can absorb molecules like hydrogen or oxygen and facilitate chemical transformations. This unique combination, noble and enduring as a bulk metal, but chemically active at the surface, makes platinum incredibly useful in industry. Platinum plays a key role in one of the most fascinating phenomena in modern physics, the spin-Hall effect. When an electric current flows through a thin layer of platinum, something unusually happens. The electron with the opposite spins are pushed in the opposite direction, perpendicular to the current. This doesn't create a buildup of charge like the normal Hall effect, but instead produces a spin current, a flow of angular momentum. Now, this happens because platinum has a strong spin-orbit coupling, a quantum interaction between the electron motion and its intrinsic spin. That makes it one of the most efficient materials for generating and detecting spin currents. Now, the spin-Hall effect in platinum is the cornerstone of spintronics, an emergent field that could lead to faster, more energy-efficient electronics. It's used in next-generation memory devices, magnetic sensors, and even quantum computing components. So platinum isn't just rare and beautiful, it's also deeply important for the future of technology. One of the largest demands for platinum today is in the automotive industry for catalytic converters. A catalytic converter is a device in a car exhaust system that helps reduce harmful emissions. Inside a catalytic converter, there is typically ceramic honeycomb coated with precious metal. And platinum is a star player in here. Platinum, along with some palladium and rhodium, catalyzes reactions that convert toxic gases from the engine, like carbon monoxide and unburned hydrocarbons. into less harmful carbon dioxide and water vapor. Essentially, platinum helps burn off pollutants at the tailpipe by speeding up the chemical reactions at a relatively low temperature. Now, this application became hugely important from the 1970s and onwards, when environmental laws required cars to cut down on smog-producing emissions. Since then, a significant percentage of the mined platinum each year goes into autocatalysts. In fact, by some estimates, around 40 to 50% of platinum consumption annually is vehicle emission control. Every standard gasoline or diesel car with a catalytic converter likely contains a few grams of platinum. Diesel engines typically use platinum-heavy catalysts. Gasoline engines might use more palladium, but platinum is still often involved. With hundreds of millions of vehicles worldwide, the need for platinum in this sector is enormous. Beyond cars, platinum is employed in various industrial processes. In the petroleum industry, for example, platinum catalysts are used in oil refineries for a process called catalytic reforming. This process upgrades low-octane gasoline into higher-octane fuel by rearranging hydrocarbon molecules. Platinum makes that possible by facilitating the chemical reactions. Now, perhaps one of the most exciting growing uses of platinum is in the field of green energy. Platinum is a critical component of fuel cells, particularly hydrogen fuel cells that power some electric vehicles and may provide clean energy. In a hydrogen fuel cell, hydrogen gas combines with oxygen from air to produce electricity, and the only byproduct is water. Platinum is used on the electrodes to catalyze both the hydrogen splitting and the oxygen reduction reactions that generate electricity in the fuel cell. Of course, we cannot ignore platinum's role in jewelry. Historically and culturally, this is what made platinum famous among the public. Platinum began to be used in fine jewelry in the late 19th and the early 20th century, once metalworkers had the means to melt and craft it properly. It became especially popular during the Edwardian and the Art Deco periods, early 1900s, for crafting intricate diamond settings. Jewelers prized platinum for its combination of strength and beauty. It has a cool white luster that complements diamonds and gemstones without tarnishing, and it's strong enough that fine prongs and filigree can securely hold stones. Platinum's durability means those tiny prongs won't break easily. High-end engagement rings, wedding bands, and heirloom pieces often use platinum for these reasons. Today, jewelry consistently makes up a substantial portion of the global platinum demand. Roughly 1/3 of platinum use per year is for jewelry. Major markets like China, Japan, and the United States have a strong affinity for platinum jewelry, particularly for special occasions. Platinum jewelry is usually 90 to 95% pure, stamped as 900 PT or 950 PT typically, often alloyed slightly with metals like iridium or cobalt to improve hardness. In popular culture, platinum is associated with luxury and milestones. Achievements, for example, platinum anniversary marks 70 years. It's interesting that something once regarded as useless impurity by the Spanish gold miners is now a symbol of the pinnacle of luxury and jewelry. Platinum's unique physical properties, especially its high melting point and corrosion resistance, make it invaluable in scientific and laboratory settings. Long before modern ceramics and advanced alloys, chemists relied on platinum equipment. Platinum crucibles, dishes, and tongues were essential for experiments involving high heat or reactive chemicals, because platinum could endure conditions that would destroy other materials. Now, furthermore, platinum is used in high-precision instruments. For much of modern history, the definition of standard units relied on platinum. In the 19th century, the introduction of the prototype for the meter was a bar made of 90% platinum and 10% iridium, chosen because this alloy is very stable and doesn't rust or wear easily. Likewise, the standard kilogram cylinder, made in 1879, was platinum iridium. Now, these standards remained in use up until very recently. The kilogram standard was only redefined in 2019 to be based on physical constant, but until then, a platinum iridium artifact was literally the kilogram. Platinum's stability made it the material of choice for these scientific benchmarks. While not as famous as gold in electronics, platinum plays a niche but important roles in various electronic components. Because it is a noble metal and a good electrical conductor, platinum is used where reliability and longevity are crucial. For example, high-end spark plugs for gasoline engines often use platinum at the electrode tips. Now, some hard drives in computers use platinum alloy in the magnetic layer of the disk to improve its data storage density. Platinum cobalt alloys can be strongly magnetic and have been used to make powerful small magnets which have applications in electronics and electric motors. In the glass manufacturing industry, platinum is used for equipment that handles molten glass. Molten glass can be extremely corrosive, also sticky to many materials, but it does not wet platinum, meaning glass will not stick to platinum. Now, it may surprise some, but platinum has important medical applications. Certain platinum compounds are powerful chemotherapy drugs used in the treatment of various cancers. The most famous of these is cisplatin, a platinum-based drug discovered in the 1960s. Doctors began using cisplatin in the 1970s and found it to be remarkably effective against testicular cancer, among others dramatically improving survival rates. Since then, other platinum drugs like carboplatin or oxaliplatin have been developed. These compounds work by binding to DNA in cancer cells, preventing the cells from dividing, causing them to die. Today, platinum-based drugs are a standard part of chemotherapy for many cancers. In addition to drugs, platinum metal itself is used in some medical devices because it doesn't corrode and is biocompatible, not harmful to the body. Platinum is used for implants and surgical tools in specialized cases. For example, platinum electrodes are used in pacemakers and cochlear implants to carry electrical signals within the body without reacting adversely. Like gold and silver, platinum is considered a precious metal for investment. Platinum bullion coins and bars are produced for collectors and investors who wish to own the physical metal. Countries like the United States, Canada, and Australia, and others mint platinum coins. For example, the American Platinum Eagle or the Canadian Platinum Maple Leaf. Now, platinum can act as a store of value, and during certain economic periods, its price can even exceed that of gold, making it attractive to investors. In times of economic uncertainty, investors sometimes buy platinum as a hedge, although gold is more traditional for that purpose. Platinum's market is smaller and can be more volatile. By now, the reasons behind platinum's high value should not come as a surprise. It's not just one factor, it's a combination of rarity, difficulty of extraction, concentrated supply, and crucial demand that makes platinum pricey. Recycling of platinum from used car catalytic converters, industrial scrap, etc. does provide some supply, and in fact recycling has grown over recent decades. Even so, recycled platinum only partially offsets the need for fresh mining, because the demand is so high. Platinum's story is a perfect illustration of how human value is assigned to materials. Here is a metal that was once tossed aside by gold miners as worthless, little silver, yet as knowledge and technology advanced, we discovered platinum's true worth. A metal of unparalleled durability, beauty, and utility. From ancient burial treasures to cutting-edge clean energy devices, platinum has woven itself into human history and modern civilization. It is expensive not due to hype or ornamentation alone, but because it generally is scarce and exceptionally useful. Now, this video was in honor of the late Tom Lehrer, maker of the Element song. This brilliant mathematician turned musical satirist passed away at the age of 97 on July 26, 2025, at his home in Cambridge, Massachusetts, as confirmed by his longtime friend David Herder. If you think we missed anything, tell us in the comments, and if you want to know more about a shiny element, watch this video about silver next.